Good day, everyone. My name is Chufeng Jiang from the Graduate Center at the University of New York. Today, I will present our work titled in Identifying Good Rules for Efficient Set Encoding of Single Constant Multiplication using Machine Learning. This is joint work with Professor Nenfa Zhou, and due to some visa-related issues, I cannot attend the conference in person, and I would like to thank Professor Zhou for presenting this recording on my behalf. Then we will go through 4 parts in this presentation. And let us begin with the single constant multiplication, or we say SCM. We consider a constraint of the form C times X equals to Y, where C is a fixed odd constant and X and Y are integer domain variables. Instead of using a general multiplication circuit, we encoded this multiplication using additions, subtractions, and bit shifts. Bit shifts are especially useful because they are essentially cost-free in the set encoding. Therefore, the main cost comes from additions and subtractions. To decompose a constant, we use 3 types of operators. The first is S plus, which combines a shift left constant with a right constant using addition. The second is S minus, which subtracts the right constant from a shifted left constant. The third is minus shift, which subtracts a shifted right constant from the left constant. By recursively applying these operators, we can represent a large multiplication using a small set of simpler arithmetic operations. Here is a simple example showing why the choice of decomposition matters. Let's say the binary representation of the example number, which is 1759, it contains 9 digits, right? So a standard shift and add method would therefore require 8 additions. However, we can obtain a much better decomposition. First, the 1759 can be decomposed into 27 shifted by 6 bits plus 31. And then the 27 is represented as 31 minus 1 shifted by 2 bits. So there comes a shared common constant, 31. And then finally, we can represent the 31 as 1 shifted by 5 bits minus 1. So instead of 8 additions, this decomposition uses only 3 arithmetic operations. This example shows that different decompositions of the same constant can produce very different encoding costs. There are 2 common measures of encoding quality. The first is min k, which minimizes the number of additions. The second one is min a, which minimizes the number of full or half adders. In this work, we focus on the min k objective only. When it comes to the challenges in the SCM problem, the main difficulty is that finding an optimal SCM encoding is NP hard. Here we focus on the word optimal. Existing optimal approaches can produce high-quality solutions, but they become very slow for the large constants. Another option is to pre-compute optimal recipes. However, storing recipes for all possible integers and bit width is not practical. And dynamic programming usually is not considered because the SCM problem doesn't satisfy the optimal substructure assumption. And then I'll introduce our previous foundation work first, which we use a dynamic approach. The main idea there is to recursively divide the binary representation of a constant into smaller chunks. When the constant is 1, we reach the base case and no operation is required. Otherwise, the method applies one of the 3 decomposition operators, referring to the S plus, S minus, or minus shift. It then recursively solves the 2 resulting sub-constants or their complements. Tabling allows previous solved sub-problems to be reused. However, if multiple decompositions are available, the DP solver still has to explore all of them in order to find high-quality solutions. This exhaustive exploration is the source of its increasing time and memory cost. And this slide shows a simplified PyCat implementation, where the first row handles the base case. The second row tries the 3 operator types and recursively solves the resulting sub-problems. Tabling reuses previous computed results, while min keeps the multiple minimum cost solutions. However, the solver may still explore all three operator branches, creating a large search tree for the bigger constants. So this leads to our main research question. Can machine learning identify good operator selection rules that reduce the search space while preserving near optimal SCM encoding quality? Our goal is not to replace the symbolic solver. Instead, we want the machine learning to tell the solver which operator branches are promising and which of them can probably be avoided. This is an overview for our framework, which contains 5 main steps, and we will go through them one by one in detail. In the first step, we use the PyCat DP solver to generate SCM decomposition plans. For example, the constant 1759 is decomposed into 27 and 31, and these constants are further decomposed until reaching the base case constant 1. The original output is stored as a text file. We then pass each decomposition equation and convert it into a structured JSON representation. Each JSON record stores information such as the operator type, the left and the right operands, and the shift amount and the current constant being decomposed. The structured representation is then used to construct graph-based training instances for the graph neural network model. In the third step, we train a graph neural network model to predict the operator type for each decomposition step. The input to the GNN is a partial decomposition graph, which contains the current decomposition and the previous decomposition history. The model then outputs a probability distribution over the 3 operator types. As shown here, each prefix of the decomposition forms one training instance, and the model predicts the operator for the next constant to be decomposed. As we can see in this example, right, we have red node, which represents the next constant to be decomposed, and we have our histories indicating by the purple node here. And in our model, we give it a field that is the history decompositions, right, to record all the history decompositions. And for the green node, it is indicating the base node there. And then we convert the model's confidence score into symbolic good rules. If the top operator is ahead of the second best by more than a threshold, we keep only the top operator. Otherwise, we keep both to avoid overproving. In our experiments, the threshold delta is said to be 0.2. And in the original DP solver, every constant may be decomposed using all 3 operator types. However, in our proposed framework, the solver first consults a symbolic predicates of the form OP parentheses C, O. This predicate stores the recommended operators for each constant. The model is not called during the search. Instead, its predictions are converted into symbolic facts. These facts restrict the operator domain before search begins, allowing unpromising branches to be pruned earlier. And this is the pipeline for step 4 and 5. The trained model produces confidence scores for the constants. And these scores are translated into a good rules file containing symbolic operator facts. As we can see here, we have constants 35, 60, 7, etc. And in the right-hand side, we have the scores for the 3 operators. And then we convert the confidence scores into predicates. Here we only record the recommended operators. For example, for the 35, we only record the S plus, as the confidence scores for the S plus is the highest. And the output remains an explicit SCM decomposition plan rather than a black box neural prediction. Here is a simplified implementation. Before decomposition, a constant. The core retrieves one of the learned good operators. The solver then enters only the corresponding decomposition branch. And for example, if the recommended operator is S plus, it calls the split PP there. The rest of the recursive symbolic reasoning remains unchanged. So the machine learning model changed the size of the search space, but the final plan is still constructed and checked by the symbolic program. We then compare 4 methods. the shift and the add as a baseline, the mini-zinc-based optimal min-k model, the original PyCat-DP method, and then our proposed machine learning DP method. The training set contains 128,767 odd constants, including all odd constants up to 65,535 and additional samples from 17 to 82 bits. For testing, we use 16 unseen constants with 1,000 instances for each bit length from 17 to 32. And it is the performance for the encoding time and the quality. As we can see here, the baseline is the fastest, but it uses the most additions. DP gives the best encoding quality, but its runtime grows quickly. And let's take a look over at the 32 bits. DP takes about 4.6 seconds, while machine learning DP takes only 0.53 seconds. This gives machine learning DP about 87 times speed up. Machine learning DP uses slightly more additions than DP. As we can see there, 8.85 compared with 7.26. However, it is still much better than baseline, right? Which uses 18 additions. Overall, machine learning DP provides good balances between speed and encoding quality. Here is the performance for the memory and the branching. As we can see there, at 32 bits, DP uses about 87.6 megabytes of memory, while machine learning DP uses only 2.7 megabytes. This is about 97% reduction. The number of explored branches also dropped from 76,000 to only 825. This explains the speed improvement. Machine learning DP prunes unpromising branches before the expensive search begins. So to conclude, this work demonstrates that machine learning can effectively guide symbolic set encoding. Our machine learning DP framework combines GNN-based operator prediction with PyCat-based dynamic programming. The model identifies promising operator selection rules, and these rules are compiled into symbolic constraints. The learned rules prune unpromising branches and improve scalability. More broadly, our results suggest that machine learning doesn't need to replace symbolic reasoning. It can instead act as a learned search control mechanism that improves the scalability of a transparent symbolic system. This is the end of my presentation, and thank you very much for your attention.